Since we have been talking about quadratic equations and we have been getting answers that involve imaginary numbers, I would like to spend some time just talking about what we call complex numbers. A complex number is any number written as a real number, either plus an imaginary number or minus an imaginary number. Keep in mind that if it is just an imaginary number and there is no real number added to it or subtracted with it, it can still be considered a complex number because we can consider the real number part being just 0. So if we do have a complex number, this is what it's going to look like. It's going to look like a real part and an imaginary part. Oftentimes the real part is referred to as A, and the coefficient on I, so the number of the imaginary part, is considered B. These below are just a couple examples of some complex numbers. So 3 minus 4i, so notice 3 is the real part, 4i is the imaginary part, or minus 4i. On the second example, I have the square root of negative 81 plus 13. When I first look at that, I might think, that's not an imaginary number, that's not a complex number, there's no imaginary part. But remember, we can't make decisions about anything until they're in our simplest form. So the square root of negative 81, as we know, is not in simplest form. If I were to rewrite the square root of negative 81 into simplest form, I could rewrite it as the square root of I times the square root of 81 plus 13. Since 81 is a perfect square, I can call that 9i plus the square root of 13. So notice I do have an imaginary part and a real part. What I want to talk about today in terms of complex numbers is how to graph them, mainly because once we know how to graph them, we will then be able to figure out where the formula for computing their absolute value comes from and use those graphs to assist us. So when we graph imaginary or complex numbers, when we graph a complex number, we are going to have the real number fall on the x-axis and the imaginary number come on the y-axis. And when we take the imaginary number, we will just take the coefficient. We do not need to take the I with it. So if I went ahead and I tried to graph this first example, 4 minus 3i, I notice that 4 is my real part, and the part that I will graph for my imaginary part will be the negative 3. So just like I would be graphing any x comma y number, I'm going to go over 4 spaces on my real axis, 1, 2, 3, 4. And then I'm going to go down 3 places on my imaginary axis, 1, 2, 3. I will then just put a point there. That point right there represents the number 4 minus 3i. If I were to graph this second example, notice the second example does not have a real part. The real part would be considered 0. So I do not have to go left or right at all. I won't go put any points on my real axis. I will just go up 2 on my imaginary axis. So going up 2 puts me here. I'm going to go ahead and put a point there. This point here represents the complex number 2i. The reason we need to be able to graph these is so we can come up with a formula for their absolute value. So if you remember from what we talked about before with absolute value means distance from 0. It generally helps or aids us in our understanding if we can look at it graphically first, so we can actually visually see what we mean by the distance from 0. If you remember back when we solved absolute value inequalities or absolute value equations and inequalities, both of those we looked at graphs first as well. So if I want to find the absolute value of 3 minus 2i, I'm going to go ahead and graph it and talk about what that absolute value means. So I'm going to go right 3 on the real axis and down 2 on my imaginary axis, and here is my point 3 minus 2i. Well, if I'm trying to solve for the distance from 0, I am trying to solve for the length of that line segment. Well, what if, using that line segment, I created a right triangle? Are there any lengths on my right triangle that I know? Well, don't I know I went over 3 and I went down 2? Could I use that to find the length of this missing side here? Well, my missing side is the hypotenuse. I know that if I'm trying to solve for hypotenuse, or any missing side of a right triangle for that matter, I can use Pythagorean's theorem. A squared plus b squared equals c squared. Well, my a can be my 3. My b can be my -2. My c will always be my hypotenuse. If I go through the solving process before actually doing any calculations, I can anticipate that in order to solve for c as opposed to c squared, once I do this calculation, I'm going to have to take the square root of each side, giving me the square root of 3 squared plus -2 squared equals c. These do not cancel. I can only cancel out an exponent and a radical, or a square and a square root, if I have multiplication. I have to do this order of operations before anything will cancel. Be careful of that. So doing that, that gives me 9 plus 4, or 13. So what is the absolute value of 3 minus 2i, aka what's the distance from 0 to the point 3 minus 2i? Well, that distance, or that absolute value, is the square root of 13. If I look at another one, suppose I have to find the absolute value of -4 plus I. Well, that tells me to go back 4 on my real or my x-axis and go up 1 on my y or imaginary axis and put a point. So if I'm asked to solve for the absolute value, I'm asked to find the distance from 0 and that point. Well, I don't know how to find the distance of that line segment unless I first turn it into a right triangle and use the distances I've already used. So I'm going to go ahead and do that. Here would be my right triangle. And I can say that this went back 4 and this went up 1. So how do I solve for that missing length? Well, notice once again that missing length is my hypotenuse. So once again I can use Pythagorean's theorem. A squared plus b squared equals c squared. And I can say my a is -4 and my b is 1. And how would I figure out what c is as opposed to c squared? I would take the square root of both sides. I do want to point something out. Notice that up here when I took the square root, I did not put a plus or minus out front. Well, if I'm talking about distance, since distance will never be negative, if I added in a plus or minus, the minus wouldn't make sense anyway. So same idea here. To get c by itself, I would take the square root of -4 squared plus 1 squared equals c. Again, I don't need a plus or minus because distance will never be negative. Well, that then simplifies to be 16 plus 1, so I get the square root of 17 equaling c. So I can either draw this out each time and go ahead and use the Pythagorean's theorem, or what if I talked about what I was doing and tried to create what I was doing as a formula? Aren't I simply taking my a, being the real part, squaring it, adding to it my b, which is the imaginary part, squaring it, and taking the square root of the sum of those two squares? So aren't I simply doing the square root of a squared plus b squared? And that's giving me my absolute value? Well, yeah, in fact, that's the formula that I can use. So I can either draw out the graph each time, or if I can understand that there's a formula and know the formula that goes with it, I can simply say that the absolute value of a plus bi is the square root of a squared plus b squared, and I have written on here c squared. So it actually should be the square root of a squared plus b squared. So please make sure and change that if you printed out the note sheet. Otherwise, you will have the wrong formula and get the wrong answer every single time. So if I look at this example, what is the absolute value of 7i minus 4? Well, I see that my a is 7, Oh, excuse me, I guess it doesn't matter because I'm adding anyway. But my A is -4, my B is 7, because I did put the real part in back and the imaginary part in front. The commutative property does tell us it doesn't matter what order we add, so it would not make a difference. Finding the absolute value of this, I'm going to go ahead and use my formula. I understand where my formula came from. I understand what my formula is, and I get -4 squared plus 7 squared. Well, that just gives me the square root of 16 plus 49, which gives me the square root of 65. As always, I need to simplify my radicals. However, I do not have a perfect square in 65, so I can go ahead and say that my final answer for the absolute value of 7i minus 4 is equivalent to square root of 65. If I look at my second example, what is the absolute value of -9i? Well, notice this time my A is 0, my B is -9. I can go ahead and use my formula. Using my formula, I get the square root of 0 squared plus -9 squared, which gives me the square root of 81, which is just 9. And if you think about where this falls in terms of the graph, I believe that's 9 lines. This is going to go 0 on the real axis and down 9 on the imaginary axis, putting me right here. So it should make sense that it's a distance of 9 units. That is how we find absolute value of a complex number. You can either draw out your graph and use Pythagorean theorem to solve for that distance from 0 to the point, or you can go ahead and just plug A and B into your formula.